So we rolled two balls at each other, and they bounced off each other in different directions. One came from the right side, going horizontal like that arrow, and one came from an angle from the left, and they collided right in the middle. And then the one on the right went off in this direction, and the other one went off in a angular direction in the other direction. The one on the ball on the left was of heavier mass and was moving faster than the one on the right.
What was the weight of that one?
4 things.
The weight of that one was.
Let's call this one Big M, and we'll call this guy Little M.
Okay.
Okay, and we'll go to our data. So this is our data from the lab. We have our ball's initial velocity over here. So this is ball. Oh gosh. This is ball 1 over here. This is its initial x velocity, which is right here, and its initial y velocity is over here. We then have initial final x velocity of ball 1 and final y velocity of ball 2. These are like the coefficients of the vectors. I guess that's how you call it, the x, y parts of the vectors.
The components of the vectors.
Yeah, the component, not coefficients. The components of the vectors. Then we have ball 2 right below it, the x and y final initial. Then we calculated the initial x momentum and initial y momentum for ball 1, which is the first one right here, and ball 2, which is this one here. And those were calculated by using our masses here and our mass here.
So we just used mv initial 1 plus mv2 initial. That's the initial, like in the x direction for each part, and we just used the momentums of both balls for each of these sets of data up here, and then these here are just the differences between final. This is final minus initial minus final.
So if you notice, we didn't actually. This is the amount of total momentum that we lost, and we didn't actually lose that much momentum, which is great because that shows that momentum was conserved throughout the collision. And what we have here is probably just error in our measurements.
Right. That's the hypotenuse, the resultant of the x and y momentum lost by using the Pythagorean theorem.
Yeah. And then we also calculated the kinetic energy, which is done over here. Let me just erase this. Don't get stuff in the way. We have our velocity magnitudes, which are the hypotenuses. So this is actually the velocity with a direction. We didn't need the direction because to calculate a kinetic energy,
right.
You don't need
just
direction.
The magnitude. It's like it's a scalar of how fast the ball was just moving.
And then we calculated the initial kinetic energy, using the same equation, 1/2 mv squared plus then the second one, so on and so forth, for the initial and for the final. And we found that we lost a lot of kinetic energy, and that was probably lost due to sound, and
also probably the when the balls collide, they're rotating one way, and then once they collide, they start rotating in a different way, and the energy gets, so there's rotational velocity, and that rotational velocity takes energy. So we think that some of the
energy
some of the energy from the velocities as they were going towards each other turned into rotational velocities as they went away from each other, which is why there's there's so much less final kinetic energy for the balls in their x and y directions at the end.
And yeah, that's it, right? Conclusion.